Have you ever looked up at a massive metal bird soaring through the sky and wondered, how does that even work? It's not magic. It's the incredible science of aerodynamics. This is the story of the invisible forces that make flight possible, a delicate dance between an aircraft and the air it moves through. It's the art of riding the wind. At the heart of flight are 4 fundamental forces, locked in a constant tug-of-war in the sky. These are lift, weight, thrust, and drag. To understand how a plane flies, we need to break down these forces one by one. Let's start with the hero of our story, lift. This is the upward force that literally lifts the plane, opposing the constant pull of gravity. The secret to lift lies in the special shape of an airplane's wing, known as an airfoil. It's curved on top and flatter on the bottom. As the plane moves forward, the air splits to flow over and under this wing. Because of the curved top surface, the air traveling over the wing has a longer path to take, so it has to move faster than the air moving underneath. This is where a famous scientific principle comes into play, Bernoulli's principle. It states that as the speed of a fluid, like air, increases, its pressure decreases. So, we get lower pressure above the wing and higher pressure below it. This pressure difference creates a net upward force pushing the wing and the entire plane upwards. That's lift. Of course, pilots can control the amount of lift. One key way is by changing the wing's angle of attack, the angle at which the wing meets the oncoming air. A steeper angle can generate more lift, but only up to a certain point. Now for lift's opponent, weight. This is simply the force of gravity pulling the aircraft down towards the center of the Earth. It's determined by the plane's mass. For an aircraft to take off, the force of lift must be greater than its weight. Once it's cruising at a constant altitude, lift and weight are in balance. This is why building lightweight yet strong aircraft is such a challenge. Engineers use advanced materials like aluminum alloys and carbon fiber composites to make planes as light as possible without sacrificing strength. So, lift gets us up, but what gets us moving forward? That's thrust. This is the forward pushing force generated by the plane's engines. In propeller planes, the spinning blades act like rotating wings. They're shaped to push air backward, and thanks to Newton's third law of motion, for every action, there is an equal and opposite reaction. The plane is pushed forward. Jet engines work a bit differently, but the principle is the same. They suck in huge amounts of air, compress it, mix it with fuel, and ignite it. This creates a high-pressure blast of hot gas that shoots out the back of the engine at incredible speed. This powerful exhaust stream pushes the plane forward with immense force, allowing it to overcome resistance and build up the speed needed for lift to take effect. That brings us to our final force, drag. Drag is the aerodynamic force that opposes an aircraft's motion through the air. You can feel drag when you stick your hand out of a moving car window. It's the resistance of the air pushing against you. There are 2 main types of drag. The first is parasite drag, which includes things like skin friction, the air rubbing against the plane's surfaces, and form drag, which is caused by the shape of the object. A boxy shape creates much more form drag than a sleek, streamlined one. The second type is induced drag, which is an unavoidable byproduct of generating lift. At the tips of the wings, the high-pressure air from below tries to spill over to the low-pressure area on top. This creates swirling masses of air called wingtip vortices, which disrupt the airflow and create drag. Engineers work tirelessly to minimize drag. They design aircraft with incredibly streamlined shapes, use flush rivets to keep the skin smooth, and add winglets, those upward curving extensions on the wingtips, to reduce the size and strength of wingtip vortices. So, flight is a delicate dance of these 4 forces. For takeoff, thrust must be greater than drag, and lift must be greater than weight. In level, constant speed flight, thrust equals drag, and lift equals weight. To descend, the pilot reduces thrust and adjusts the angle of attack, allowing weight to become slightly greater than lift. This elegant solution wasn't discovered overnight. It's the result of centuries of human ingenuity, courage, and sacrifice. Early pioneers like Otto Lilienthal, the glider king, made over 2,000 successful glider flights in the late 1800s, proving that heavier-than-air flight was possible. Sadly, he paid the ultimate price for his passion. After a fatal crash, his last words were reportedly, "Sacrifices must be made." His work inspired others, including two bicycle mechanics from Ohio, Wilbur and Orville Wright. The Wright brothers realized that control was the key to successful flight. They built their own wind tunnel to test different wing shapes and developed a system to control their aircraft, its roll, pitch, and yaw. On December 17, 1903, they achieved the first sustained, controlled, powered flight in history. It was a moment that changed the world forever. Since then, aircraft design has evolved at a breathtaking pace. We went from early biplanes with lots of struts and wires creating huge amounts of drag to the sleek, streamlined designs of the 1930s with monocoque fuselages, where the skin itself bears the structural load. Then came the jet age, supersonic flight, and the continuous quest to make planes faster, more efficient, and safer by mastering the forces of aerodynamics. And this science isn't just for airplanes. Race cars use aerodynamics to create downforce, essentially negative lift, which presses the car onto the track, increasing its grip and allowing it to corner at incredible speeds. Spoilers and inverted wings are designed specifically for this purpose. Even in rockets, aerodynamics is crucial for maintaining stability during the fiery ascent through the atmosphere. The space shuttle, for example, was a masterful piece of aerodynamic engineering, launching like a rocket and landing like a glider. Ultimately, nature is the true master of aerodynamics. Look at the incredible agility of birds, or the streamlined body of a peregrine falcon, which can dive at over 200 miles per hour. Scientists and engineers are constantly looking to the natural world for inspiration, a field known as biomimicry. So the next time you see a plane gliding effortlessly across the sky, remember the beautiful symphony of science at play. It's the story of lift, weight, thrust, and drag. It's a journey from the ground into the endless blue, made possible by our understanding of the fundamental principles of flight. We've learned to master the wind and, in doing so, have given ourselves the gift of the skies. Thanks for watching, and don't forget to fly high.